This is the first pure astrophysics lecture. Now what do I mean by that? It's the first time in which we will be using what we learned until now to find out about the rest of the worlds. And I mean worlds, not our own world. So far we figured out how to find distance, period, Kepler's and Newton's laws, properties of light, and now we'll use mostly properties of light to find what stars are made of and how the universe as a whole works. Soon enough we will even encounter that famous Einstein's formula E equals mc squared. Energy equals mass times the speed of light squared. Note that we have skipped chapters 4 through 8. These are about the solar system constituents. That's covered in Baker's class PC-141, the solar system. So, we are now in chapter 9 and we will also cover chapter 10 this week. This picture is a picture of the sun through an H alpha filter. This means that out of the whole Roy G. Biv colors of the sun, out of the whole red, orange, yellow, green, blue, indigo, violet colors of the sun, only orange light at exactly 656 nanometers between wavelengths comes through the filter. Well, otherwise our retina may be burnt. Let me apologize for the grinding noises in the background. That's my puppy grinding on a bone. Yeah, seriously. Sorry about that. Anyways, at this point, it would not be a bad idea to have several of your PowerPoint presentations open at the same time, or YouTube's. I will refer to the other lectures and the assignments as well. What we know is in the table on this slide. But how we know that is the question that I asked even in the very first lecture. For example, how do we know the first value? Well, you guys did that in the few lectures, the first few lectures, using values from the Aristarchus of Samos method. Basically what you did is you found the distance to the sun. First by looking at Earth as a pizza, if you recall, then the distance to the moon with lunar eclipses, then a little bit of trigonometry for the distance to the sun, and then we found out that the sun covers basically about half a degree in the sky. Remember, you can actually cover your sun with your pinky. Don't try it at home, cover it with your whole hand, but it doesn't take the whole hand. Use that, make a circle around you, and you'll find out that by using a simple 2 pi r argument and part of the 2 pi r, lots of pizzas, you can find out the size of the sun. Next, the mass. Look at page 39 in the book. Reworking Kepler's third law using Newton's results, as we did in the homework assignments that you had due this week, can yield a mass. That mass in the homework assignment was very large. So is this one. How about the density? Well, take volume, take mass, divide the mass by the volume, and you get density. Density of water, for example, is 1000 kilograms per meter cubed, which is exactly like 1 gram per centimeter cubed, which some of you may have taken in chemistry in high school. Well, guess what? The sun is not really dense. It's just over the density of water. Earth is 4 times as dense. There are also spots of the sun. These are called sunspots. And they survive for many days. So we see then that the sun itself moves, and that's how we deduce the rotation period. There are more of them every 11 years, following a mysterious 11-year cycle. Oh, and the surface temperature? That's from the rainbow spectrum, or the rainbow black body radiation that we learned in a previous lecture. Luminosity, that's also from that lecture. So, the sun is a ball of fire with total luminosity of about 410 to the 26 watts. That's 400 trillions 100-watt light bulbs. A 100-watt light bulb is those wasteful incandescent light bulbs that light the living room. Over on Earth, every square meter, that's about 9 square feet, gets about 1400 watts from the sun. No need for light during the daytime, right? So, as you can see, the sun is very bright, even very far away, 93 million miles away. Hence we know how powerful it is. So, how do we know about the composition of the sun? The fact that the outer layers are called the photosphere, and that's where most of the light's coming from. Outside of it, a chromosphere, transition zone, and a corona. Inside, a convection zone, radiation zone, and a core. Of course, we see nothing underneath the photosphere, so how the heck do we know that? Interestingly enough, you can find out about the corona during an eclipse, but also with X-ray telescopes and even satellites that go pretty close to the sun. We've done that. Chromospheres can be investigated with a prism on top of a telescope. So the same is true for the photosphere. Then the convection zone and the core, interestingly, are investigated by investigating earthquakes on the sun, or we should better call them sunquakes. I love this picture. Click back and forth and notice what's going on. If you look underneath the pictures, it has a symbol with U, V, and all those kind of things. Of course, V is for visible, U is for ultraviolet, X for X-rays, etc. All over our book, pictures have the exact same designation so that you understand that not all of them are taken in visible light. Both of these pictures here are not taken in regular light. The first one is invisible, but in the visible, and the second in UV/X-rays. But even the visible picture is not purely what the eye see, but what special cameras see. In the first, the sun is eclipsed by the moon, and you can see some areas that are brilliant, that are just seen through craters on the sides of the moon. In the second, there is an artificial eclipse by a satellite. X-ray pictures and UV cannot be taken from Earth's surface. They have to be taken from above Earth's atmosphere. And so that had to be done with an artificial satellite that created artificial eclipse. Cool. You can see how active the sun is. This was taken during the most active period of the sun a few years back, including a coronal mass ejection, which is an amazing phenomenon. No, don't worry, it doesn't mean that the sun spews so much matter that it can slam into Earth and destroy it. Even those things that look humongous are very, very thin in nature. It's the solar photosphere that has most of the material and the radiation. And of course, the rest, the inside of the sun, has all of the material. Guess what? On this slide we also see two pictures. Click back and forth. In the first one, we basically see the light through a prism, but we broke it into 4 stripes. Take it and make it into one long stripe that follows RGB, red, orange, yellow, green, blue, indigo, violet, and that's what we got from the sun, just that we kind of spread it along so that you can see the difference. The second one, we get even more details. What I mean by that is that, for example, you see that there are lines that are dipping in, and there is an overall spectrum that kind of peaks in the middle. That is the spectrum of the sun when we take the absolute brightness. Of course, this tells us where the biggest brightness is. The wavelength is in both places in nanometers. That's the distance between wave crests in nanometers, in billions of meters. So far, those spectra and X-rays and UV pictures help us see everything that you can see until you hit the border of the sun, the photosphere of the sun. In order to see further into the sun, there was an experiment called gong experiment. Basically, like a big gong, the sun vibrates in many modes. The modes that are kind of red and blue on the left-hand side of this picture basically create small earthquakes. Would those earthquakes go through the sun? That's a basic question. If they do, you'll get slightly different pattern than if they don't go through the sun. And that depends on whether the core is solid or liquid or certain kind of gas that undergoes turbulence or certain kind of gas that undergoes something called the radiations. That's how we found out the internal structure of the sun. So now, let us describe the sun from the inside and towards the outside. In the very inner regions, there is something called the radiation zones. The biggest question that took almost 100 years to determine was what makes the sun run. What's the sun's central engine? Ends up that it's a nuclear furnace that turns E from mc squared, meaning some mass is turned into some energy, and that's the energy that keeps the sun from collapsing and keeps on radiating warmth that keeps us alive. How that works will be the topic of our next lecture. Outside of that, there is turbulence. Basically, it's kind of like a spaghetti pot. There are regions that are very, very hot, so they rise up, and they rise in kind of circles. If you boil spaghetti, you see how the spaghetti kind of rolls around. That's what is done in a convection zone. You reach the outside area, the photosphere, where everything is still boiling hot. Temperature in the middle is 15 million degrees. Temperature of the photosphere is only a mere 10,000 Fahrenheit or 5,700 degrees Kelvin. Outside of that, we have chromosphere, transition zone, and the corona. That's it for today. Have a lovely time. Live long and prosper.